Let's get started. So we'll send out the peer review assignments out later this week for homework 1. We'll wait for anyone who hands it in late. Homework 2 will come out next week, maybe late next week. We'll give you some time off, but we want to get it together. Definitely get Cython installed soon, so start asking how to do that. I know now 2 people in the room at least have Cython installed. Who else has managed to get Cython installed and run like the Mandelbrot code? Well, I mean, if you get it installed, make sure that actually you can like run the previous examples. If it produces a picture, it's working. Anything you run into when you try to do that doesn't work, let me know. I'm going to put up, hopefully today, maybe tomorrow, a repository that will have some Cython code in it and also have some OpenMP code within the Cython, because we probably have to install an OpenMP knowledgeable compiler on at least some machines to get access to the low-level stuff. Right, so you should have. So if you installed it in the VM, then you should be good. But it's good to make sure. So we'll get out a test repository that will allow you to go through that installation pain before the homework comes out. No class on Monday, holiday. There'll be a reading for Wednesday posted to Piazza today. Maybe a couple small things. All right, so it was like not very many people at Cython, okay. I do emphasize, try to get it soon. Try to run the Mandelbrot tests that we were talking about in class. Feel free to do that, while we're talking here. Okay, today we're gonna talk about locks, using locks, the cases where you need them, show some examples in Python, just in pure Python code, just for experimentation, not worried about performance right now. But you'll need them for homework 1, you'll need to think about communication between processes and scheduling things for homework 2 and for homework 3, and in general, anytime you're doing multi-processor things. All right, why do we need locks? And the most obvious one is shared resources. Wait. Sorry, this is an old version of my. Guess we'll do it here. Okay. Control access to shared resources. Something that if you're writing to a file, for example, only one thread should be able to do that at once, or you're going to start interleaving problems. Guarantee valid state in shared structures, particularly complicated ones, trees, dictionaries, where if one thread goes in to modify the shared structure, at some point in a list or something like that, you're going to probably make something invalid, right? You're going to have a temporarily invalid state. And if you don't have a lock, you could be preempted. That thread could be preempted. Another thread will come in, try to access that state, and hit something that's not valid. This is the reason for the GIL, right? All of the Python structures are basically shared in threads. You don't want to modify a dictionary and leave part of it hanging and have some other thread come in and try to use it. So yeah, so a tree so for example, if you're doing something like, let's do a list, something even simpler, right? I want to prepend to a list, for example. Well, maybe list is not good because you can get around that in various ways. Well, so there's contention for shared resources, right? Where someone could go in and modify a list. We've seen examples of this before, and we'll see some more here, where someone could, if one thread is modifying a list, another one comes and tries to modify the same list. If you don't have some sort of lock protecting it, then you can easily end up with something invalid. But suppose you have a list that includes 2 things. It has both the head pointer, right? And has something like also the length, right? to save you having, which Python does have, right? Length is an order one operation on lists. Pending to it, though, could take, usually order, could take the length of the list easily, because it's, to reallocate or something like that. And so I come in here, and I have to update one or the other of this shared state at the same time if I'm appending a new thing, right? I'm gonna have to either come down here and put something on the end, at which time if I say length 4 and then I process, I say, okay, how many items do I have? I will process that many, I will get to here and I'll stop even though there's more to do in the second thread, for example. Or I update the length first, and then when I go to process it, I say, okay, length is 5, but I don't get a chance to do this part in the first thread. The second thread comes in and says, oh, the length is 5 items, boom. See, so it's, there are ways around this, especially for appending or things like this where you can just write a pointer all at once when it's ready to be valid. But if you have a more complicated structure than something like a very flat list or a simple binary tree, at some point you're gonna have to update 2 pieces of information to be valid, and a preemption in the middle could occur. If that preemption, if you don't have some sort of lock, someone else could come in and look at that data while it's in an invalid state. So there's also, and then the final thing is, sometimes we have an algorithm where we have multiple things communicating. We need to use locks to make sure, not just that the data structures that they're sharing are valid, but that the algorithm behaves correctly in cases where we need to make sure that, for example, one thread is working on one piece and waiting until, and then other threads are waiting until that work is done before they proceed. So shared resources, just for some examples of these. Output, network, display, file, read. There's a quote. The original quote is based on regular expressions. And I think I posted on Piazza, basically, some people, when they see a problem, they think, oh, I'll use regular expressions, and now they have 2 problems. Some people, when they see a problem, they say, oh, I'll use threads, and now they have blah, 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 right? And so we can see this. It's very easy. Let me pull open. Very simple. Oh, come on. All right, I'm just going to start up 4 threads. I'm going to have this little function that just says, okay, hello, 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 from the thread index. And I'm going to just go for 5 seconds, all right? And there are a little bit of some details here that are Python specific. Not really Python specific, but implementation here. I'm going to set the threads to daemon equal true. So when I do this, I start off running, right? Python starts running, it has 1 thread, the main thread. And then I'm going to create 4 new threads. I'm going to set them all to daemon. What that means is when Python will exit when all the non-daemon threads are done. But daemon threads can't keep Python open. If I don't do this, those threads never exit, right? They just sit there spinning, and so Python will never exit. It's not critical, I just don't want you to get confused by it. That is just there so that Python will exit after the main thread is done. All right, what happens when we run this? Right, we see all kinds of interleaved. I mean, most of them manage to print at least out the whole line before getting preempted, but often you get on the, this return was delayed from, this extra return was delayed from that thread, or possibly one other one, all right? And you could easily imagine if I were trying to write out something consistent, I'm not gonna do a good job there, right? So let's see the most obvious way to fix this. Okay, so now let's get a lock to prevent standard out from being written over multiple times by the same thread, or by different threads. So right here, we've got the threading module. Let's just get a lock. It comes in, it's unlocked by default, and we'll pass it as an argument to the threads. So now each thread up here still spins, but before it can print, it has to take the lock, right? Then it's allowed to write. The with statement basically says, grab the lock, do this block of code, release the lock, okay? So we're just gonna have the lock, print out our message, go on, let the other threads run. Now everything looks pretty clean. All right, good. Do notice, however, we're not getting a lot of thread cycling here, right? It's almost always big blocks of thread 1, 1, 1, 1, 1, 1, thread 2, 2, 2, 2, 2, 2. That's just because the Python doesn't switch very often, the Python scheduler. All right. Quick poll. How many people are actually doing this at the same time? Just wondering. Are you just watching me type? All right. I encourage you to actually run with these, play with them, throw in the locks, take out the locks. It's a lot more effective. I mean, you can watch me do it, but learning by doing is a lot more effective. And probably more exciting, not that we're at a high level of excitement here. All right. That's the basic case. One of the most obvious uses of locks. Keep shared resources protected from trying to overshare. How do we choose what to protect in shared resources? And how finely do we subdivide that protection, right? So we get into, you probably heard of coarse and fine-grained locking. So there's another example in here, increment table. It's basically just gonna take, I've got a table of like 5 elements. Actually, I'll just bring it up. Okay. So each worker is just going to sit, again, in a spinning loop. It's got a queue. We've seen queues before talking about multiprocessing for communicating work. It's going to get it some index and some value. It's got a table that it was passed in as an argument. That's going to be a shared resource. It's going to pull the old value from the table. It's going to sleep for a while to simulate work and allow preemption, to not allow other threads to run. And then it's just going to increment the table value, right? I could have done this with a plus equal, but I want to force more switching here. I want to simulate a slower resource or some computation that needs to be done. And then right here at the end is something useful with queues and when you start doing multi-threading stuff. I can basically say, okay, I took a job from the queue and I finished it. Down below that allows me to do this. So I create the thread, same thing. Here's my table. Starts out with just 5 elements. With 0 to begin with. I go through and I 100 times, I say, okay, increment some new value in the table by 1, and then I do queue join. That allows me to wait for all the work to be done. I've put a bunch of work on the queue. I want to wait for the queue to be empty. Queue join waits until that queue count is 0. Or until the task done, I've seen as many task dones as I did messages. Yes. Okay, so the question is, how is the GIL interacting with what we're doing here? Yeah. So I'm forcing unsafe behavior in the threading code. I'm not forcing unsafe behavior. The GIL is only there to protect Python's internal structures. Anytime between any 2 statements, the GIL can be released and some other thread can run. So up here in my worker, I take the old value from the table. I've got the GIL the whole time I do that, right? I get the old value, or I change a value, or I insert a value into a hash table or an array. I resize an array. All of those, I've got the GIL. I make the change, and I still have the GIL. I might release it there, but I'm not going to produce an invalid array structure. But the GIL only protects me within Python instructions. It's only to protect Python's internal data. It doesn't protect me against things like this. There's nothing that says there's nothing that prevents a thread from preempting me while I'm within this stream of instructions happening here. So when I pull the value there, I'm holding it in a variable, right? And then later on, I'm going to put that old value back plus whatever my increment was. If in the meantime, someone comes and modifies that particular table index, which is likely, given the sleep in particular, I'm going to put back the wrong value, right? So I take out 5. I'm going to add 1 to it to get 6. Meanwhile, I sleep. Another thread comes along and says, oh, 5. set it to, I increment it. Maybe that thread comes back before the first thread, sets it to 6. I come back and I set it to 6. What should I have set it to? 7, right? We both incremented by 1. So the GIL doesn't help here. It makes sure that the array is always valid and that basically my Python code won't crash internally. But the GIL doesn't protect us from multi-threaded programming within our own, basically violations of sharing or protection of shared data structures at the higher level.
So threading.thread class, that's not a Python object?
The threading, it is a Python object. It's an actual thread running through Python. It's just that no thread will run during any other thread, but they can wait. They basically switch off. So the execution trace looks something like this. The program starts and runs some Python instructions, okay? And then it creates a new thread, or possible multiple new threads, okay? And they have some timeline. So maybe my first thread still executes some Python instructions and then gives up the GIL, and something else executes some Python instructions and gives up the GIL. And then maybe this one runs, maybe this one runs again, and then this one. None of these will ever overlap, right?
What's the point of multi-threading then if more than one can't run at once?
Right, yeah, exactly. It doesn't speed anything up, right? There's still cases where this is useful, particularly if you're waiting on slow resources, right? If I'm doing a web crawler, I can launch 100 queries in the time that it takes and process queries very quickly. But if I send out a request and wait for data to come back and process it and send out a request and wait for data to come back, that's going to be really slow, right? Because I'm taking that latency. You can still use it for latency hiding. So this lecture is not about efficiency. That will be when we start talking about OpenMP and getting down into the Python code where we can give up the GIL. This is about why we need locks and how we use them in multi-threaded code. It applies to that low level as well. But it's more, we're just demonstrating at a high level why this is needed.
If that's the structure, then where are you overriding, like incrementing incorrectly?
All right. So if this is what the structure looks like, where do things go wrong? Okay. So suppose this one gets an increment. It says increment value or table 0 by 1, and suppose the value at that point is at this point is equal to 5 right here. Okay. So that thread is running in that loop. And it's got a private old value because that's a local variable inside the function. So it's just to that thread. So in here it sets old value equal to 5, right? And then it goes to sleep, right? Let some other thread take over. This one gets the same message, increment element 0, okay? It says, okay, I will set my old value equal to, what is the table value right now? Still 5, because I haven't run that later increment instruction. So old value equals 5, and it sleeps. But suppose it doesn't sleep as long. Right? There's a little bit of noise in there. It says, okay, my next instruction is table 0 basically equals 6. Right? So at this point, table 0 is equal to 6. Now this one wakes up. What's its old value? 5. Old value is still 5 here. So it says, okay, table 0 equals 6. Right? So we dropped an increment. Right? So that's where it happens. It's that in-between statements. And I'm forcing it here to make a point. I'm doing this sleep. But if you're doing computation, even if you're not doing computation, I could force it to happen. I could just let this run without any sleeps, and eventually there's going to be a handoff between threads, between those two instructions, but it's less likely if I don't actually sleep.
I know you explained it before, but what is the queue doing?
The queue is just a thread-safe communication. It's a FIFO. And it's multiple readers, multiple writers, multiple readers. In this case, down below, work is being fed in right here. Right, 100 times, put 100 little messages on the queue. Basically a work queue, go do this work. Up above, there are I've started 4 threads, and they're reading from the end of the queue, or the output of the queue, saying, take a message off. And the queue is just useful because it's thread safe, and it can handle multiple readers. So no message is going to be read more than once. I can safely have multiple threads writing to a queue. Okay, it's just a nice inter-process communication. It's basically message passing with some protection. Okay, it's one of the message passing options. It's not the only way to communicate.
Two questions. So that example you just gave makes complete sense. Can you give an example of where, if the GIL weren't there, something else worked?
So the question is, if the GIL weren't there, how could this go even worse, or how even go more awry? Okay, suppose I have implemented, suppose I weren't incrementing the table. Suppose I were making it grow, okay? And let's assume underneath that the tables are implemented, which I think our lists are implemented as a block of contiguous memory. One thread comes in and says, okay, append to this list, right? Set the new value to this. It says, oh, I need to allocate more memory. So it allocates some memory, and yeah, especially let's consider if it stores both a length, like the current length, and the memory. So it comes in and says, okay, I need to increment to length 10. I'm not big, I'm too short. So it says, okay, new length equals 10. I allocate a block of 10, so I have a pointer and I have this count. I say, okay, length equals 10, and I'm going to assign, and then I'll assign the new block of memory, all right? Suppose another thread comes in. Between those two steps, I say, oh, new length is 10, but I haven't actually given it space. The new one says, okay, I'm gonna put something, great, I've got a list of length 10. I haven't actually assigned the memory yet, though. It's still pointing to like length 5 or something. The other thread comes in and says, okay, I'm going to write something at point 10. That is somewhere else. That is, I mean, it's either, maybe I don't crash. Maybe it just goes someplace that I don't see the value. But certainly, I haven't actually written anything to anywhere useful, right? I'm about to just get rid of that memory. So that's what the GIL protects against, is the internal Python state. Q.join doesn't actually start it, so I call thread.start. The threads are spinning before it gets to there. They're not spinning, they're sitting on the queue. The queue, when you read from a queue, you wait until there's a message if there's nothing there. The Q.join, it combines with Q.taskDone. So when you're using queues, you want to put a certain amount of work there. Q.join allows you to wait until all the work is done. Because, right, if I didn't do something here to wait for the messages to be processed, right, I'm going to put a bunch of work. They're going to start processing that work, and then the main thread is going to be like, oh, I'm done, right? This is, wait till all the queue is empty. Wait till you've done all the work on the queue.
So if you didn't have Q.join, it would print out like stuff.
Let's see. Well, okay, so let's hold that. What if I didn't have the Q.join? Let's see that when I actually put in the locks. Because right now, it's not going to give us good results anyway, right? People, so we've talked about how this is going to go bad. Let's see how it goes bad. What file am I doing? Increment table. All right, so I put 100 messages on there. Each one was increment some location by 1. And at the end, I just print out the total and then how much time it takes. Okay. 93, not the right answer, right? It went fast. That's good, I guess. At least it produced the wrong answer quickly. Okay, so now we have a choice. We need to protect the table entries, right? So the default and the simplest usually is let's just protect the table. Let's do a coarse-grained lock. Let's lock the whole thing. All right, we just lock large pieces of state. This is not necessarily a bad choice in your programs. Databases often do this, just lock the whole database while someone else is doing something, particularly if someone else is writing to it, only allow one writer in the database at a time. You might have a whole library that you just have one lock for, especially if you're not going to be in that library very often, it's fine. The GIL is an example of a coarse-grained lock, locks all of the Python interpreter. Linux 2.0 was the first multiprocessor version of Linux. I was there, I remember. Had one lock. The entire kernel could only run on one core at a time, and it was very slow. And in fact, it got slower the more the more cores you had. Often its performance was very bad. And parts of that remained until version 2.6. So for a long time. I mean, they started adding fine-grained locking. But this was the right decision. Before that, it was a single processor kernel. Couldn't do it, or could only run on single processors. This allowed them to work on multiprocessors and then start breaking off pieces for other locks to do a better job, and now it's quite efficient. So this made it very simple. So let's look at the coarse-grained version of this table problem. All right, so down here, I'm going to create one lock. And then each thread is going to get the queue in the table and the lock. All right, so there's one shared lock before I create all the threads. And up here, I just do the obvious thing of, okay, grab the lock before you do anything with the table. I'm still sleeping the same amount. I'm still doing all the same work. I'm just going to grab the lock. What's the downside right here? Right. Well, and the other thing is, do I let go of the lock when I'm done sleeping? No. I still have the lock. So the other one ran pretty fast. Gave a bad answer. Ran fast, though. Right? This one will looks correct, right? Let's find out. What? Why does it not give up the lock? It gives up the GIL, but it can't give up the lock because it's got the lock. I've got state that is, well, I'm not outside. The sleep is within the lock, right? It doesn't give up the lock. When it starts sleeping, it doesn't give up that lock. Right? Now we got multiple locks going on.
When we're talking about this one.
That lock is not given up just because I slept.
Right, but when you're done sleeping, the lock.
Yeah, okay, so yes, as soon as it reaches the end of this block, right? But before I had 4 processes, and the work that I was simulating was they're all sleeping at once, right? So the sleep times were overlapping, right? This time, I'm in a lock. Every other process, every other thread, where is it going to be sitting while I have the lock? Waiting for the lock, right? Not sleeping, not doing the simulated work, not doing real work, sitting up there. And so all my locks are now, all my sleeps, all my work is serialized, right? This is the problem with coarse-grained locks.
So before in the argument thread, there was, you still had like nothing in the dot, but you still have to have a comma, nothing.
Right here.
Yeah, in the argument. Yeah. So here you have lock, but before you had like comma.
Oh, I had this.
Yeah.
This,
Is it regular, right?
well, it's more just a habit because then I can always, this is exactly the same thing. It's a tuple of 3 elements. The only time you actually need it is if you want to make a tuple of 1 element, right? I want this to be a tuple because it needs to be a tuple to be passed to the function. So if you need a tuple of 1 element, that's how you write it. And then because I was adding arguments, I just kept on putting commas. All right. So this was just why do I have an extra comma or not an extra comma sometimes. Comma at the end of a tuple is just nothing. All right. So this one's going to lock. It's going to protect state within the table. It's still going to do the same amount of work in terms of the number of additions. But much slower, yeah. Correct answer. 100 messages were received. 100 increments were done. Everything's fine there. Let's go back to the question about what if I don't wait on the queue? Okay. So the queue, there's this queue join down at the bottom, which every time you put an element on a queue, there's a counter that's incremented for the queue. And every time you call this task done, that counter goes down by 1. And it's a shared state. It's protected with a lock in the queue. So it's safe, thread safe. Queue join says when the counter is, wait until the counter is 0. Okay, so let's take that out. Oh, now it's really fast, right? So what happened was the master thread, the main thread, said, okay, create all this work, create all these threads and set them to go, right? And they all start waiting for work to appear on the queue. The master thread then says, okay, put a bunch of messages on the queue. That happens very quickly, right? So it basically puts 100 messages on the queue and then doesn't wait for them to be processed. So the workers have just started getting messages. They've taken a value. One of them has, because we serialized it with the course lock. One of them has taken a value. It's sleeping, and the master is like, oh, I'm done. Print out the answer, exit. And this is where that daemon, non-daemon thread thing gets in. So it exits immediately. It doesn't wait for the work to be done. That's why that's there. With non-daemon threads, what would happen actually is it would never exit. So if we didn't set them to daemon, daemon basically says this thread cannot hold Python open at the end. And this is the same as in Java. Java has threads exactly like this. This is general. In fact, the threading module is based on Java's threading. So it should be very similar if you've done that or if you're going to do it in the future. The daemon says you can't, if I don't set it to daemon, then it never exits because those threads are in a while loop, while true loop, right? They're always sitting there until, I mean, no one's going to put messages for them. They're going to be sad, but they're just sitting there, so it won't actually exit. Okay, so as you might imagine, the opposite of coarse-grained locking is fine-grained locking. So you lock individual items or substructures. The overhead is higher, right? You've now got, if you're going to start, before you had one lock, now you have n locks for n pieces of state. So you take up more memory, and you have more locking because you have to do more, basically more locking is going on, there's more checking. You're generally, instead of doing just one lock at the entry to your function, for example, you're going to do 20 locks throughout the lifetime of the function call or whatever library. So there's more overhead. So the example here, we have a lock. So here I will create a bunch of locks. I create the table, has 5 entries. I create 5 locks. Just I'll lock each element independently. Everything else is basically the same, except in the worker, where instead of just getting a single lock, I now have a set of locks. And now I lock based on which index I'm working with, right? There's no communication between indices in this problem. There's just, I work with one index at a time. So that I can do this instead, right? Grab the lock for the table index I'm working with, go on for the rest. And then again, do the task done.
Is queue doing something similar to this? Because you said queue can also handle multiple writes at the same time. Still produce correct answers.
The queue is doing something very similar. It probably, in fact, I think it's written in pure Python. Oh no, but it has extra, so the queue, the question is the queue doing something similar? And the answer is yes, except queues also are also shared multiprocessor style. And so underneath they've got some shared memory things going on. But otherwise, yes, very similar. You could implement your own just thread safe queue as a list, right? When you put in something, append it, and take from the beginning when you read. And just lock, right? I think from what you've seen here, you have enough information probably to build a queue that would work with threading. There's a little bit more with task done and checking accounts. There are other primitives that are useful for that in the threading library. But yes, exactly. It has a lock. Only one person gets in there at a time. Okay. So this one, the locks, we'll have a lock per element. And hopefully, now the code looks correct. Let's see how it does. Question?
How does thread figure out that there is one lock per table?
So the question is how does it know that there's a lock per table entry? I'm being explicit about that. So right here, right, I set up the table, and then after that, I set up a lock per element in the table. Right, so now I've got an array of locks.
This just means that like, you do as many locks as like elements in the table.
Yeah, I can't write it the same as, like table I can do, this times notation. That's just take a list and then stitch it together 5 times, right?
Would it be the same if you do like for I in range 5?
Yes, it would be exactly the same. What I can't do is, I have to do something like this, because what happens if I do this? This is an easy Python bug to make, maybe. Doesn't call, right? It calls threading.lock once, puts it in a list, it makes 5 copies of exactly that lock, and I'm back to single locking. I'm back to the coarse grain lock, I've just made 5 copies of it, right? So that's why I need something like this. This way I only have to, this is cleaner to do it this way. Underscore is just a variable name I don't care about. But this way I only have to, if I want 10, I just do this, right? And everything still works.
So thread figures that out if you have the same number of blocks as number of entries, then it would be 1 block per entry.
No, I had to figure that out. So what I do is I create an array. I've got my table. It has 5 entries. Let's make it 10 entries. That's fine. 10 entries. Yeah. And then I make a lock per entry. I create a lock per entry, and down here I pass that table. It's basically a list of locks. I pass that list of locks into the worker, and up here, when I'm working with it, I get an index, and I lock that index. All right. So.
So it's stupid. You need to tell.
Yeah, I need to tell. Okay. So. Okay, 2 things. Correct answer. That's good. Second thing, faster. It's almost as fast as the wrong answer, right? Which is good, like it's correct and fast. It'll be consistently slower though, because I'm still have this overhead for locking, right? It also has sort of, this is a good example to play with. What happens if so I'm putting the indices on here, right? In a way that is very cooperative with the locking structure, right? Because I put an index, and then the next message is the next index. So one thread reads the first message and locks the first index. The second thread reads the next message and locks the second index. So there's no contention for the locks here, and that's why it speeds up basically as fast as the one with no locking. If I play with the message order here, for example, if I do all the increments for the first element first, this will be very slow, right? Because they'll get a message, they'll say, I need that lock is busy. There are ways around that, but Q is not the one for that.
So the fastest time will always be less than the serial time.
Fastest time will always...
I mean, like they're about the same as the serial time. Right?
You mean incorrect time. You mean the incorrect version. Because the incorrect version was threaded.
No, but I mean, like, since only one thread runs at a time, this should be no faster than just running this.
No, this one does allow parallel sleeping. So so the coarse-grained one, all the sleeps were serialized because they were, right? So let's go back to the course. The question was, okay, all right. Okay. So coarse-grained, fine-grained, they're in-between grained as well. Trade-offs. Coarse-grained, it's high contention, right? So low concurrency. You have a bunch of threads, they're all waiting on the same lock. You can't have a shared resource that's hit by a bunch of threads. But the code is very simple, right? This is the Linux argument. We'll just put in a big lock, we'll make things work later. Fine-grained, you get very high concurrency, you get very high performance. That's what Linux and most things are now. But the overhead goes up. You've got a lot more locking. Instead of just locking once and going and doing a bunch of work and letting go of that one lock, you lock and you unlock and you lock and do a little bit of work and unlock. And you get complex and buggy code. Threading code is very easy to write in a way that causes problems. Lock problems, right? There's overhead, there's contention. Those are the obvious ones. Then there's a whole list. These are the 3 sort of most common problems, but it's the number of ways to write bad threaded code is basically the number of ways to write bad code times the number of threads you're using. Deadlock and starvation are very common. Priority inversion we don't have to worry as much about, but it's an important one to know about for other programming paradigms. We'll talk about it. So deadlock. Two-lock example. Now I've got this move stuff. I'm basically gonna have two workers, or some number of workers. I have two tables. And they're each trying to take the work off their table and put it on someone else's table, right? Classic. So they're just gonna sit there, they're just gonna sit and loop over table A, which is their table, and try to move things from A to B and make B deal with them, right? Meanwhile, B is doing the same thing in the other direction, right? There's gonna be a bunch of work just shifting between, or a bunch of items just shifting between these two tables. So you can see right here, right? I'm gonna take something off of table A. If I actually have something, I'll take something from B, I'll increment it, and then I'll take one off of mine. Right? It's like my children doing their chores. Okay. So I'm gonna create four threads. So they're gonna be two taking from A and two taking from B, right? And all I do is I just swap their args right here. If their thread index is even, they're moving from A to B. If their thread index is odd, they're moving from B to A. Start them up. And then I'm just gonna, there's no queue, there's no work being done. I'm just gonna let the main thread run for a while and print out the sum of the two tables, right? And if this code were correct in a threaded sense, those two sums would always add to the same amount, right? I'm taking from one and I'm putting on the other and vice versa. So the sum should stay the same. But as you can probably guess, without any locking, that's not gonna happen, right? 84, 27, like, not only are they moving it from table to table, they're just throwing it away entirely, right? Is it obvious why that's happening? It's the same problem here, right? We pull off an index, and then we write it back without protecting our state. And so at some point, it starts to drop, okay? All right. Deadlock. It's one of the most common locking problems. So right here we've got thread 1 needs resource A and resource B, right? The two tables. Thread 2 needs resource B and resource A. And so they use locks to acquire them, right? Right, this is what we do, shared state. And they try to acquire them in that order. How's that gonna go? Come on. Apparently I just deadlocked my system. What did I hit? That's classic. Power button doesn't work. I think I have no mouse. I can click. All right, that's awesome. I'm super pleased with that. What's gonna happen? Let's go to the board. While my machine tries to, oh, it's back already, hold on. Predictions. Right, right. So it's gonna be, I'm grabbing them in the order that I think I want them, right? I'm gonna grab table A, or I'm gonna grab the one that corresponds to my first table and the one that corresponds to my second table. Where I'm gonna grab from where I wanna do it. So one of them's gonna be, no one touched table A, and the other one's gonna be, no one touched table B, and then they're like, okay, now I need the other table to change it. And the other one's like, I want the other table to change it. And then they just stare at each other. Also like my children doing chores. All right. I think it's upgrading my OS. No, okay, there it is. Ignore, quit.
Running that example looks like there's sometimes they do share information.
They do manage to go a little bit, sometimes they manage to get a little bit ahead.
How does that happen?
So there's no sleep in there, right? In that one. So what happens is the first one starts to run.
So basically both tables have been locked and they can't talk to each other.
Eventually that happens, right? All right. So let's run it. Yep. So they'll sometimes do a little bit of work, not usually. They usually deadlock pretty fast, but what can happen is the first thread gets in there and quickly moves a bunch before the second thread arrives. Okay, and so the totals change here, right? So that's what happened here is the first thread moved a bunch over to the other side, and then eventually the other thread arrives and locks, and it has to wait until you get a preemption, basically a switch of threads, when one lock is head but not both. Okay. Reopen, yes. Okay. Let me make this big. There's a pretty easy fix for this, actually, in a lot of systems. So right here, sorry, I didn't get to show the code. So all I did, I had the two tables, A and B, and I create a lock for each, right? And then I do the obvious thing, pass the locks, right here. You know, give the first couple give the even threads A, B, lock B, and then generalizing from that, give the odd threads B, lock A. But up above, where they use the locks, right now each of them, this A, B is now an alias. I should have used different names. It's basically A is where I'm moving from, B is where I'm moving to. So it first says lock my table, then lock the other table. But different threads are going in different orders, right? And that's why we deadlock. You can avoid deadlock as long as whenever you have multiple locks, particularly nested locks, always lock them in the same order. And in fact, if you give your locks an ID, you can guarantee this. If you give them an index when you create them. You can guarantee this, and anytime you have a lock, if you try to lock a lock of lower number, you just crash. Guarantee that it won't happen. This one will work.
You say like with lock A and lock B, or is that?
Not by default. David Beasley has a nice little, like very small, he has a little write-up with a little class that says, you know, wrap the locks in something that's ordered, and then allow me to lock multiple ones. And complain if I ever try to do this lock A, lock B out of order. And otherwise do them in order. So if I just swap those two locks, now when I run deadlock, we can see the work is shifting back and forth and the total is always 90, always the same. I mean, so because it doesn't deadlock, because if you have the first lock, no one can go in and try to grab the second lock. You always grab the upper lock first before the lower lock. Okay. There's another one though that can happen, which is starvation. So thread 1 repeatedly just calls some long running function while it holds the lock, and thread 2 calls some fast function. Like if thread 2 could get the lock, it could give it up very quickly. But if they share that lock, then thread 1 will almost always dominate, right? It'll hold the lock for much longer. Even if thread 2 gets it for a little bit, the number of calls that go to thread 1 will be much higher. Or the amount of time, sorry, the time spent holding the lock. So I simulate that here with sleep time argument. It's basically the same thing. It's the non-deadlocking version, or just it's got a global lock. And then it sleeps. I'm just going to create 2 threads. One of them sleeps for a full second. One of them, since it's the thread index in range 2, one of them gets a 0, one of them gets a 1. So one doesn't really sleep, and one of them sleeps for a full second. And they're otherwise doing the same sort of work. It's a coarse lock on the 2 tables. And what we see here is not necessarily that it doesn't work, but look how slowly the numbers change, especially compared to what was going on up there when they were locking both tables. Here it's not much work is happening because almost always one thread is moving things. And it tends to also move in it also tends to move everything from A to B, right? Because the one that moves back doesn't get a chance to run very often. Okay. One more problem to talk about. Yes, question? That's depending on how fast, well, depending on your version of Python, in fact, because the scheduler changes from version to version. That could, so you're saying that basically everything was moved from one table to the other. You might need to decrease the sleep time. Basically what happened is the slow thread managed to run enough to move everything over, I think. And it should be the other way, yeah. Let's talk about that after class. It's more complicated than that, actually. Maybe I'll post on Piazza the explanation. It's going to tend to move one way because the slow thread doesn't get as many calls in, actually, before it sleeps. All right, starvation, we just talked about. Don't have to worry about it in most of our Python code, but preemption and locks can be, is a serious problem, or can get very complicated. And because what happens is, okay, you have some unimportant thread, and you have some important thread, and they share a lock. And so the usual way to deal with this is somehow make it so that when the important thread says, I need the lock, the unimportant thread says, oh, okay, I'm sorry, I'll give it up. I'll stop, you go ahead, and then I'll get it back later, or I'll fail in my task and restart. Especially in real-time operating systems for things like robots or car control or things like this, so Google Car. You get this problem called priority inversion, which is also surprisingly common. What happens is if you've got some important thread, it has the lock. And the important thread says, I need the lock, the one that makes you stop without hitting pedestrians. Meanwhile, the ones like turn signal has the lock for some reason. So you have the code that says, okay, when the important thread wants the lock, the unimportant thread should somehow give it up. But there's some medium important thread, more important than the unimportant, but not as important as high. It preempts it, and it preempts it for a long time. Something somewhat important, but running for a long time. The unimportant thread never gets a chance to run again, to give up the lock. And so it just sits. That's what happened with Mars Pathfinder. It was resetting every day, like full system reboot. They didn't know why, and it was causing a lot of problems. It was a priority inversion. There was an unimportant task. It was like, look at the sky. Is the wind blowing? The very important one was move data between modules on Pathfinder. And then there was this medium importance, not as important as looking at the sky, but communicate back to home, which takes a long time. And so what was happening is meteorological observation was starting, communication was starting up and preempting that task and then running for an hour or more. And never was data getting transferred. This is probably the best, besides Apollo 13, this is maybe the second best NASA hack. Like, they just have the best. They had launched it with a real-time operating system, but it had this debugging interpreter still there, where you could type in C code and execute it. And luckily, there were some variables that they could set globally to fix this. Basically, to raise the unimportant task's priority when something waited on its lock. And so they dumped into GDB, typed in something, boom, mission saved. And then it runs for 10 years past its expected lifetime. Right? Didn't look good at the beginning. All right, other primitives in the threading module: semaphores, events, conditions, a few others. They're not many, and they're all pretty simple, and they're all just based on the Java primitives, and they've been around for a while. Just look through the threading module document on python.org. It's worth it. It's short, has some nice examples. Some of these will be useful later, not just locks, but some of the other primitives. That'll probably be part of the reading, actually, is to go through that. You don't have to comment on it. I just want you to actually read it. All right, next time, a poll. You'd like to learn about OpenMP and Cython? OpenMP is sort of the low-level C multi-core threading library. Or would you like to talk about problem 5? OpenMP. Okay, no one wants to see problem 5 again? I'm seriously considering, based on the reading that I'm going to assign, making problem 5 part of homework 2.
Again.
Same data.
Well, just
give you the correction? Okay, we'll see. We'll discuss. All right, we'll see. This reading made me unhappy about Spark that I'm about to post, okay? It's not going to make you any happier about it. It'll make you more knowledgeable, though. It's going to build character. All right, so we'll do OpenMP next time. Okay.